So welcome everyone to our first talk on joint math physics seminar at Dhaka, and we are all over the globe. And thank you everyone who is attending. And I again apologize to all of those whose time cannot be matched despite of giving their valuable opinion. So today I'm going to talk about a covariant quantization in curved spacetime. This is no way my original work. So I have mentioned some references. These are, of course, bare minimum. There are also classic references that I haven't mentioned, but I thought it's best to start with uh, simple things because it might be technical at some point. Let me start with our very basic quantum field theory. So the usual setup in physics is in a Minkowski spacetime. So which I just denote R4 because it's isomorphic with a dot, which denotes Minkowski uh, scalar product. And I will use this signature minus, plus, plus, which doesn't matter what on you choose, just for concreteness. And as customary in physics, we represent a point in Minkowski, say x, and then there is time, spatial component with a underscore, which basically means t x1 dot x3. Okay, so now more or less the way quantization started, at least historically, and more or less this standard setup is that we have some quantum field given by capital Phi at some time t and x, and then we have its canonical conjugate field P at same t with some other spatial point y minus this P, sorry, pi dy P dx equals to I. I like to color, so let me allow some fancy color. So this is the Dirac delta, and that's called the canonical commutation relation. So in some formalism, at least in physics, we start from this formalism. You can also start some like while relation, but more or less you can go back and forth. There are advantages of both way. Let's stick with that. Later, I will comment about other issues. So this is called equal time commutation relation. And then from here, we can use Fourier transform. So we can write a quantum field in terms of Fourier modes in R3, where we use the creation and annihilation operator depending on what your test. So the x, I will write in a minute what is there, and then Hermitian conjugate something, and then 2 pi cube to something m square root. So force of polar familiar, what is something? This is just a momentum p, and this is also p. This is also p squared. Okay, and now from this data, we can go to say any spacetime point. So px, which is e to the power I t something, again 0x minus it something. Again, expert knows this is our favorite Hamiltonian operator. And then one can compute p of x, p of y. Okay. Now, that's kind of the initial setup that I have told. Now, there are some issues that are conceptually problematic if you look closely. So that the first canonical equal time canonical relationship is telling that we are literally probing a quantum field at a point of space and time, so at a particular time, fixed time and a space, which means we can probe point-like distance. In other words, it means we need actually infinite energy to probe such thing. And if you pour infinite energy in your space-time manifold or R4, it will be curved, it will create black hole or even maybe drive to quantum gravity regime. So conceptually, this is not a very physical thing to start up, but still we can argue, okay, this is our setup and we end up the compute correlation functions. So why to care much about this? But there are situations when one needs to care. For instance, if we consider quantum field theory under external field, then the Hamiltonian is not conserved. And then one can't use this blue prescriptions by Hamiltonian to get space-time quantum field. But still we can argue, okay, if we don't get space-time, at least we have spatial or equal time computation relation. But that even doesn't sufficient for certain situations like non-equilibrium dynamics, when a system literally drives with time, and then there is no hope with equal time, because non-equilibrium means evolving in time. Okay, and then we can also think about why we should just stick with Minkowski. We can couple with classical gravity. So it means that I'm not quantizing gravity, provided there exists quantum gravity theory, for instance, superstring theory, loop quantum gravity, and many more. But at present, none of this theory can be taken this very low energy limit so that it reproduce our standard model of particle physics or cosmology. So you can think this quantum field theory in curved space-time as a combination of quantum fields incorporating effect of classical gravity. Okay, and now immediately we'll say that, okay, if I use this equal time, there is no notion of time in a Lorentzian manifold or a specific point of space. So how about general relativistic covariance? So what this property tells that it is not really a good idea conceptually or also for addressing certain physical situation to start from equal time commutation relation. And now there are some mathematical issues. So the usual setup in physics is that quantum field, like the phi, this is an operator. And now from linear algebra, we know if there is an operator, we have to first tell, okay, what is the vector space or some space? And
I'm
then
sorry, but are we allowed to ask question right now or
anytime,
afterwards?
yes,
Anytime.
anytime.
Okay, then I have a question. So you are saying like in curved space time, there is no concept of time. So which I interpret like if you think about 3+1 decomposition, I can take any manifold and just decompose it like 3+1 way.
Mm-hmm.
So always I will have an infinite spatial slice denoted by a particular instant of time.
Mm-hmm.
So why is that? Why I don't have that thing in curved space time? Can you please elaborate?
Yeah, there are two reasons. First, that you have infinite choice. So if you want to define time this way, you have infinite way of defining time. And why should
But they should be kind of related through coordinate transformation, right? So that's not a problem.
no, that is problem if you are considering non-tensor quantity. So everything is not tensor. For instance, quantum fields are not tensor. Green's operators are not tensor. So if you go to different coordinate, then there is no Lorentz transformation, just diffeomorphism in GR. So if you do a diffeomorphism transform, then only which has nice coordinate transform property, like tensors, for instance,
Yeah, yeah, I
it
understand what you're
works,
saying.
but everything will not. And then there is another big problem. So you can do this sort of foliation, but you cannot always do such a way that it can be interpreted as time. To interpret something as a time, you need actually a time-like killing vector field,
Yep.
a global time-like killing vector field. Now, not every Lorentzian manifold admits a global time-like killing vector field. And this situation is also important for cosmology. For instance, if you look at de Sitter, which is Lorentzian manifold, but it doesn't admit a global time-like killing vector field, or Robertson-Walker, because there is initial singularity due to classical gravity or some other reason, but you can't just extend globally this notion of time-like killing vector field. And the
Okay.
subset of manifold where you can do it is called a stationary spacetime. So if you confine yourself in a stationary spacetime, then everything is perfect. You have notion of time because you have canonical time. You don't have a time coordinate, but you have a time flow, which is sufficiently good to define Hamiltonian, and you can carry on.
Okay, great. Thank you so much.
Okay, you're welcome. And now some mathematical issues. So we need to tell about what about the vector spaces where this operator is acting on. So is some Hilbert space, and these are infinite dimensional Hilbert space. So they are not isomorphic to some Cn. And since they are not isomorphic to Cn, which is the case for finite dimensional case, you have to tell which Hilbert space. Because if I take a different Hilbert space, mathematically they are different operator. Now one can say, okay, these are mathematical artifacts. Maybe it doesn't have any physical consequence. I will come back to this question, perhaps end of this talk. But now there is another very serious mathematical issues, which tells that the way we interpret quantum fields in physics, this is a function of a space-time, which is an operator valued function. As you see, this the green part is written nice functional way. But if you look at the right-hand side, there is Dirac delta. This is no way a function. So what this equation is mathematically, a function is equals to a distribution, which is impossible. So either you have to change the Dirac delta or the quantum fields. Now we know that from numerical experiment done so far, this if you start from this way, then we compute right correlation functions. Standard model of particle physics is the burning example. So that means the red part is actually more and less right thing. We have to change the left part, the green part. And that basically tells that quantum fields are not really function of space-time. They are distribution. And these are two of the things mathematically that I will address in my talk, apart from this conceptual issue I have discussed. So let me start with some preliminary of space-time. So by a space-time, I mean a Lorentzian manifold Mg. So G is a Lorentzian metric. And since G is a Lorentzian metric, we have causal character, which doesn't present in a Riemannian case. Namely, we can have a time-like vector field. So I call time-like. So G is a metric and X is a vector field. If it is negative, because my convention, then it's called time-like. If it is 0, then it's called light-like. And if it is positive or the vector is itself 0, then it's called a space-like. Now these two is called causal character. And these are very fundamental characteristic of a Lorentzian manifold, which is never present in a Riemannian setting. So what this basically tells that if you take any point in your space-time, say X, you have two cone. One you can say past cone, I denote it by J minus, and another you can say the future cone.
Sorry, can I just ask a question?
Sure.
In the Riemannian case, of course, this inner product is 0 if and only if the X is 0. But in the Lorentzian case, of course, because the inner product being 0 doesn't mean that it is 0, the vector is 0. But the third option, it's space-like when it's greater than 0 or X equals to 0. I don't understand the X equals to 0. How is, if X is 0, then, how can Gxx be greater than 0?
No, it's or, I mean, either there is a non-zero X for which the inner product is positive,
yeah,
or X is 0. I mean, there are some classification where they put X equals to 0 separately.
and that's considered space-like.
Yeah, but I have put together because anyway, I am not So causal character is what is more important. So just
right. I mean, x equals to 0 means that
it's basically zero.
the
So
separation
zero
is
vector field.
the separation is 0, right? Yeah.
Yeah, it's just a zero vector field everywhere. So it's not something very interesting. Yeah, thank you. So now by a space-time, we mean that this sort of light cone structure is possible every point in your space-time, and the future remains future and past remains past. So the blue part will be always upward, the future, and the green part will be always downward, the past. And if this is true, then it's called time orientation. And by definition, in space-time is a Lorentzian manifold. So I again denote by same mg, but which has to be orientable plus time orientable. Okay, so now we have our Lorentzian spacetime, and now we want to formulate our equation of motion. So since I am going to only discuss scalar field, so this is Klein-Gordon equation. So I denote by box. So box is defined by minus divergent gradient plus some parameter m square plus some coupling lambda and Ricci scalar. So which is then first second order differential operator from smooth functions on M to itself. Now this form is not usually what available in physics. So what we do, we choose a coordinate chart, xi, x mu, and then this form is nothing but g mu nu. So I choose Levi-Civita connection, nabla mu, nabla nu. So I think that's more familiar form, but keep in mind, this is only true chart-wise, globally only the first equation. And if you are in a Minkowski, then this is just partial derivative and then usual wave operator. Okay, so far so good. Now our Klein-Gordon equation is just u v plus 0. So we want to quantize something which satisfy also this equation at this level classically, but we want to demand it quantum mechanically later. Okay, so now to formulate this thing, this conceptual and mathematical problem, we also need to solve this Klein-Gordon equation. And in some sense, this Fourier decomposition we use, it comes from this thing, because if you write this also satisfy classical Klein-Gordon equation and then you quantize using mode function expansion.
Sorry, can I just interrupt and ask a question?
Sure.
Can you tell us a little bit more about the origin of the Ricci scalar term in your operator?
Yeah, so it comes from like you have classical gravity, and now what is the most general form of a wave operator you can write on a Lorentzian setting? And then you see that there's the most general form. And if you want to think physically, then what's the effect of gravity on scalar case? It will just curve our space-time. And now there are several notions of curvature, like Riemann curvature, Ricci curvature, so on. But we want something scalar, right? Because this is a scalar equation. So what's the notion of curvature? That's
Sorry,
right.
so
I see.
Sorry, go ahead.
Yeah, so there's the intuitive idea of why Ricci scalar is showing up. And if you want to derive more mathematical way, then you just say, okay, I just want to write a wave operator and ask what is the most general potential term I can write, provided I have diffeomorphism invariance, and that's the form. And you see, if you
then why cannot you have R mu nu, say R mu nu, higher order terms, scalar from higher order Riemann tensors?
Yes. So if you want higher order, like R squared term, yes, you can. So now for this talk, I want to keep everything in the level of linear. So because I mean, of course, that it can be, and there are literature on that. To handle non-linearity, it needs a bit more about distribution theory, which I am not planning to go more, but I am happy to talk maybe later. So everything is a linear. So I don't want to do anything non-linearity, neither quantum level okay, classical level, you can say there is.
So what do you mean by linear? Linear in the field?
Yeah, in the linear in the field like phi, and also this question like higher order curvature like R square. I think it's called Kirchmann scalar. So of course, on
Right.
include Kirchmann
Yeah, yeah.
scalar. So yeah.
Because the Ricci is not, it's not linear in G, but I understand. Yeah, okay.
Yeah, because G will not enter in the equation. So something scalar. Yeah. So Kirchmann scalar can be a candidate. Okay.
I want to raise the issue.
Yes.
Okay, the way you define divergence dot grad, like G mu nu del mu del nu. I mean, like, are you assuming that G is covariantly constant? Because you can also define it as nabla mu G mu nu nabla nu, right?
Yeah, I have chosen Levi-Civita because it's a Lorentzian setting. So there is a canonical choice of Levi-Civita. So it's covariantly constant without loss of generality. Now you can consider torsion if you like. Again, it's not like this framework is not applicable if you include torsion. Of course, it's just some higher, some different term will show up, but the structure will be same. So still it's a wave operator. Wave operator with a torsion, nothing else.
I see.
But yeah, it has physical significance and phenomenological aspect, but structurally there will be no change because I will not use this specific form. Yeah. Okay, now one way to solve wave equation, in particular any differential equation, is to construct Green's function. So Green's function are not really function, these are operators. So let me just recall a bit. So G, I will write something later, is a mapping from compactly supported function on spacetime manifold to smooth functions on the manifold, such that this is kind of inverse, which means that if you add box G identity and the other way, so if you start this way, so you have to just restrict in compactly supported section, it will be also identity. Okay, and now we have at least two Green's operator, so retarded, advanced, and support of this retarded advance applied to some function is just J plus. So in my convention, retarded goes for plus and minus for advance support of U. So if you remember this picture, so one drives everything in future, another drives anything past. Yeah, so that we know, just written in a mathematical way. So out of these two Green's operator, we can construct another Green's operator, which has several names, like causal Green operator. Historically, Pauli and Yoder consider it, so it's also called Pauli-Jordan Green's operator. Just tell whatever you like. Okay, and now I would like to use something from partial differential equation theory, which called if a operator has certain property. I'm not going to utter all the details, but this property is satisfied for Green's operator, then one can write an integral kernel. What is really meant by that? So G, no matter what is here, U is a function of X because of the mapping property, can be written as an integral over M of a distribution. So X, Y.
So sorry, can I interrupt? And can you show me the support of G retarded and G advanced again, pictorially?
Yeah. So
if
this is G retarded.
Yeah, where? Right. So is there an overlap between G retarded and G advanced?
Only, yeah, it can be. Like for instance, if so it depends on why it is acting. Say for instance, it's acting here. So then G retarded will drive this way.
Yeah.
And G advanced will drive this way. So
the
it can.
So the minus would be the little bit of a that region which looks like a diamond, right?
Yeah. So in general, if you have a nice, then it will be exactly a diamond region. So
what I want to know is that the G which is a difference between G retarded and G advanced. What is that region? That region is the
Okay. So
shaded
the
region.
G is so in general, for wave
Yeah.
operator we have a answer where is the support of G, but in general we don't know. For wave we know, and I will write shortly. Okay.
Okay.
So
Sorry,
okay,
I don't
so
understand the question of Tibro, sir. What he was saying about
what
the
is support
diamond?
of G? What is support of causal propagator?
Okay.
Okay. Okay. Okay. Now, okay. So this calligraphic G is called integral kernel, which is a bidistribution. So I am not sure whether distribution theory is well known to everyone, but if you are not familiar, let me just give a glimpse. So yeah, what a distribution does. So usually for a function, if I write f is a function, it maps a set to some different set. So it takes a, say for instance, a number and it maps to another number. And now for the case of distribution, it will take a set, but it produce a number, C or R, depending on your model, okay? So I will give more concrete example in the context of quantum fields. So for the time being, just keep in mind the difference between function and distribution is that function maps to a number to another number, where the distribution maps to an element of a vector. Sorry, it's not S, it's element of a vector space. Sorry. So say it's a C infinity M. So it takes a function and it gives a number. Okay. We'll see concrete example a bit later. So this is a bidistribution. That means it will take two functions. It will eat two functions and give two numbers. So in this form, it has eaten the one function, if you can. So it has eaten the u. So if you look at the variable, and then it gives just another function. Yeah, you see, it maps function to function. Okay, so the main point is that this integral kernel exists for Green's operator. And now why this is important. So again, let's go to Minkowski case. So in Minkowski, what we do, how do you solve wave equation in Minkowski? We do Fourier transform. What do we do? We write G, again, it can be advanced retarded, whatever, x minus y, 1 minus 1 by 2 to the power 4, depends on your convention, e to the power I, p, x minus y, g tilde, something which is a function of p and dp. And this is subject to the condition that p squared minus m squared g tilde equals to 1. And as a consequence, what we get is that g retarded advanced in momentum space is 1 by p squared minus m squared. Now again with fancy stuff, p naught plus minus pi epsilon square. Okay, so we have advanced retarded and we have subtract, and then we also get causal propagator. So let's do it for a Lorentzian setting, and we can do it. Why? Because there is no Fourier transform in a manifold. So if there is no Fourier transform, we cannot write the first Fourier representation or Fourier transform. And if that is not possible, we cannot get this p square minus m square sort of constraint that got here. And then what we did, we just shifted the pole such a way that one is advanced, one is retarded, and also there is Feynman and Feynman, but let's not go there. So everything starts because we know the pole structure very precisely.
Can you, sorry, can you just give us a qualitative insight into why there is no Fourier transform on a general Lorentzian manifold?
I am just going to tell this. So why it is not trace. So let's see what is here. So this is P. P belongs to basically also isomorphic to R4. And this is also Minkowski. So that we have an inner product space to define a Fourier transform, or at least Euclidean space. Yeah, because we need to have this product structure. Now on a manifold, X is a point of a manifold, and there is no notion of X minus Y on a manifold. It doesn't exist. And now how P got, we get this momenta or generalized momenta. So this basically belongs on a manifold in the cotangent bundle. So you can't really perform anything because one thing is living in a cotangent bundle and another thing is in a manifold. So it's just not defined at all. What one can do a chart. Yes.
I think we do define something we call bitensors. These are 2-point functions, like, and you can take like coordinate minus coordinate things.
Yeah, I am coming here. So you can take coordinate, like you. So what is meaning by coordinate? You take a chart, and then everything you map to Rn or Rd, and then everything is very nice. So why not do we do this thing? I'm coming here. So you can try to do this thing. Okay, very well. So there is this question, and then what's the problem? Problem is that Green's function, or which is actually an operator, is not a function, first of all. This is not even a tensor. This is something called Fourier integral operator, which is a very complicated object. And if you want to do this thing, in general, it takes very high level of analysis. And this is up to some extent possible. And that's called Fourier integral operator theory, which does this thing. But if you just take a chart and try to glue it up, it will not work. What you need more, you have to know the singularity structure, precisely this thing. Because when you glue a chart, then you are gluing such a way that your smooth condition or differentiability condition is preserved. Now, at this kind of singularity, because this is in non-invertible points, like p square equals m squared, the hyperboloid are the non-invertible point. You need to know where this is the non-invertible point or where this cannot be inverted. So if you know this point very precisely and globally, yeah, because this is a global information, not a local information. One chart, this might be true. Another chart, it might not be true. So you can never attain a global information. In general, you cannot get a global information from chart. So provided you have a global structure of singularity, and then you can glue it, and still, if you have, it's a very hard work, but it is possible. But even that is not possible in this setting because we don't have a global structure of singularity. But the other way, it is actually possible. And that's what I am now going to talk. So now we want to have a global theory of Green's operator on a manifold without using the chart, or you can use chart provided you have all these ingredients, okay? And it has actually a classical result by Hadamard in the beginning of 19th century, and then Rees, and then lots of people. And finally, the result is that if you are in a general Lorentzian manifold, there is no Green's operator. So very sad news. And then what we should do? Now people actually looked how far one can push this result of Green's operator existence and, if possible, uniqueness. And the answer is that you have to restrict the space-time geometry. And the restricted class of space-time geometry is known as globally hyperbolic space-time. So what are these sort of space-time? So this is again a Lorentzian space-time such that you can foliate this thing like this time foliation we were talking at some point. Okay. And then these are kind of time-like curves. So this class of manifold tells that you always have a time-like curve, but it is not killing. Okay, that's important. So that's why you cannot interpret as a flow of time. So it's not killing, not necessarily killing. If it is stationary, then it's killing.
Can I ask a question, kind of more of a general knowledge question?
Sure.
Is it not true that for a space-time to be a solution to Einstein's equation, it has to be globally hyperbolic?
Very good question. So first answer this question locally. So you can ask if there exists a local solution of Einstein equation, provided you have given all the Cauchy data. Answer is yes, provided space-time is globally hyperbolic. So you are right. Now you can ask, is it true globally? There are some results by Gerosh and Schoke-Brucha, and then other also working right now. And so far the answer is, at least it has to be globally hyperbolic. And then some sort of global solution exists under certain condition. So not most general situation, but yes, again, without global hyperbolicity, there doesn't exist a global solution of Einstein equation. In fact, it is true for any wave type equation. So if you have a wave type equation in a Lorentzian manifold, the necessary and sufficient condition to have a global Green's function or solution is global hyperbolicity. In fact, this way it was invented. So there were mathematicians who are working on PDE, like Jean Leray, and he invented the idea of global hyperbolicity trying to solve PDE. On the other hand, in Cambridge, there is this group of Penrose, Hawking, and all these people, later continued to Gerosh and Wald. So there is a famous theorem by Gerosh which tells that a Lorentzian manifold is a global hyperbolic provided this is isometrically isomorphic to R cross sigma with a metric from beta dt square minus some ht. Ht is a Riemannian metric on each Cauchy slice, and beta is just called lapse function, which tells that when you go forward in time, you not necessarily going straight, you can go like this way and that way, and this beta basically accounts how much you are deviating. And that's really, as this question, yes, it is true, you need global hyperbolicity. And then there is famous work of Penrose, that the cosmic censorship. So and there it tells that if you forget about initial singularity of Big Bang, if that happens, then only physically admissible solution of Einstein equation, not Einstein equation, in fact, Einstein general relativity is globally hyperbolic spacetime. So this is really very general class, and which has very different motivation that it is actually a very good class of Lorentzian manifold. And then there is more philosophical reason. So you can ask, can we have closed time-like curve? Which means that something can come back, like time machine or sort of thing, classically. And in a Lorentzian manifold, it is possible. A Lorentzian manifold admits closed time-like curve. And now we have never observed something. So it's natural we don't want those things. And that will destroy causality immediately. And you can ask, okay, what is the condition we don't have such thing? Answer is global hyperbolicity. So globally hyperbolicity is kind of the canonical setup in mathematical GR or PDE. So yeah, we also assume it. So now we are in a happy situation. There exists advanced and retarded Green's operator for a wave equation on a globally hyperbolic spacetime. And this is unique. So this is really a beautiful result. And since these are unique, we can immediately construct causal propagator by retarded minus advanced. And now, if you look at how this is constructed in Hadamard's work, then Hadamard basically did this very high level of analysis, like considering the singularity, this and that. But this singularity was not obtained. Sorry, just let me finish. Using this sort of first writing Fourier transform and then look, but there is more global way to characterize singularity. And he used that thing, and later Hurmander propounded this work. Yes, please.
So basically, are you saying that if the spacetime is globally hyperbolic, then we can foliate this spacetime? I think I don't understand the picture that you draw in the previous slide. That you said that there is no reason to assume a killing like time vector, but there is a flow of time. Can you please explain?
No, there is no flow of time. This is just a time-like vector field. So by definition, a space-time is time orientable. And
Okay.
if some spacetime is time orientable, there must exist a global time-like vector field, not killing, global time-like. So by the very definition of time orientability, you have a time-like vector field.
I see.
And so in global hyperbolicity, basically that enters. It's nothing new information. Only the new information is that you have this Cauchy foliation, which tells that every time-like vector field intersects this Cauchy hypersurface only once. That's why you don't have. So you can't have this sort of situation like this, not possible. Okay. And that will destroy causality. And also you don't have any of this result. Okay, and be careful. So global hyperbolicity is really a global condition, right? Because you can always get some Cauchy surface. Like you can look at the last Cauchy surface and then it's everything fine. So to understand global hyperbolicity, you really need a global condition. So this is really global, not only by word global. This is a global. And if you look at Penrose's original work, he actually imposed and also Garrosh this condition to understand GR in a global perspective. And also true for Larry's work on PDE. Okay, so now back to the question raised, what is the support of causal propagator, this G in the Lorentzian case? So the answer is that if we are given Cauchy data, say K, K0, K1, since it's a second order differential equation, we need two initial conditions, the Cauchy data K0 and K1. Then we can actually write any smooth solution in a unique way using this causal propagator. How? So we write this integral kernel. I just say Green's operator, K1 of y, d volume H of y. So this H means this Riemannian metric H. So every Cauchy hypersurface comes with a Riemannian metric. This is called Garrosh splitting theorem. So this is the measure with respect to the Riemannian metric minus, again, integration here. So we need some unit normal vector field along sigma, because we need to give the initial condition, and to need the initial condition, we need kind of the first derivative, and n basically gives the idea of first derivative in a global fashion. So nabla n xy k naught and then d volume h naught. Okay, so now you see why the causal propagator is so effective. Basically, you have Cauchy data, and then causal propagator gives you a solution without doing any Fourier transform. So this is kind of the global version of what we know from physics literature. And now question is that what is the support? So support of U is, so I just made a bit terminology. So I used J to mean J plus union J minus of X, okay? So it's basically taking whole thing by J. And now support of U is equals to J.
Sorry, could you just explain the expression for U of X very briefly? I can't read the handwriting. So
Sure.
just very quickly. First is the integral kernel of the Green's function, Green's operator, and then what's that?
So this is one of the Cauchy data, K1. This is a Cauchy data because you need.
Oh, I see.
And this another Cauchy data.
Okay. And the second one is that is the normal is the boundary is the normal derivative of the
vector field. Yeah, covariant derivative with respect to normal vector field.
And the normal is along the Cauchy Cauchy hypersurface.
Yeah. So you can think like coordinate is just the first derivative term, like t.
Right.
Yeah.
Okay.
So now what is the support?
Hello.
The support is in.
Can I ask a question?
Sure. Carry on.
Please.
Okay. Sorry to interrupt. I'm just an undergraduate student, so pardon me if I'm asking something wrong. So it's been mentioned earlier by you that space-time is hyperbolic, but what's the discussion about space-time acts like a fabric? is there any connection between these two concepts?
I don't know what is meant by a fabric. Could you tell the context? Like what is mean by a fabric? I mean, feel free. It's not like you have to tell very high level definition. So just what is your intuitive idea of fabric? What is a space-time fabric?
Snigdha, do you want to address that?
Onirban, can I intervene?
Yes, yes, sorry,
This subject.
my mic was muted. I'm sorry.
Oh, sorry. Go ahead, please.
It's like space. I seen actually a video or read some, I think, paper about it. It's like we think that space time is linear, but according to that fabric theory, it's like it's very flexible, and everything in space are just field of energy, and it's I think I don't think I can understand, I can tell about it very vastly, but it acts like a fabric, like how a fabric is flexible, and when there is a ball on it, it make it curvature.
Okay, in that sense, it is. So what do you mean by that more precisely? Your if you look at here, you see, so this is a manifold. Probably you have learned or you will learn at some point, and G is the metric. So this fabric means this metric varies from point to point. And if this metric varies, there is two notions of curvature. This is called intrinsic curvature and the extrinsic curvature. So by this, as you telling that it is a like elastic or fabric, means that it has the intrinsic curvature. So it may go down or up at some point, but it depends. It's not embedded, just intrinsic. But maybe there are more in this context of fabric. So if you are fabric by only by this concept, then it is already encoded here. So by a manifold, which metric varies at every point of a manifold, means that you are allowed to have continuous deformation, or at least a smooth deformation, which is, physically speaking, is a fabric. Yeah.
Thank you.
Welcome. So yeah, now we return to the question, where is the support of G? And in this context, for a wave operator, the support is in future and past both. So this is J plus, this is J minus. So what this G does, if you take something from here, it drives things forward and backward in equal footing.
So is it a Feynman propagator?
No. So for Feynman propagator, it will push forward only positive energy solution and backward only negative energy solution, or the other way you want to define. But what causal propagator does, it will not distinguish between positive or negative energy solution. It will drive both without understanding whether it is positive or negative. There's the difference between causal propagator and Feynman propagator. Yeah, but everything drives in a causal light cone. So no information is leaking in some sense out of light cone. And global diversity basically ensures this thing.
Sorry, Onirban, can you just repeat this, what the answer you gave to Jawad again? I think it's kind of important.
Yeah. So if you look at Feynman propagator, what it does, it pushes, say, positive frequency solution to forward in space-time, and the other way for negative frequency solutions. In contrast, the causal propagator doesn't distinguish between positive or negative. So you give something here, it will just push it backward.
Sorry, where?
So anything. So say this is your Cauchy data, okay?
Right.
And then it will push backward, whether it has positive energy or negative energy, doesn't matter. And at the same time, it will also push forward, whether it has a positive energy or negative energy, doesn't matter.
Okay, I see.
Okay, so that's actually very important distinction between Feynman propagator and causal propagator. Okay.
Is the Hadamard boundary condition, when we're doing the Feynman propagator, there's a particular integral you have to do on a
Yes,
the
yes,
on
yes.
the
And that's
complex plane. And is this a Hadamard condition that you have to do here?
Okay,
Or no?
so for Feynman propagator, you have Hadamard condition or Hadamard something called wave front set, like a singularity structure, but it is not done by Hadamard. It is done by Doströmer and Hurmander in a very historic paper. So they basically settle down what is a Feynman propagator for a general wave operator in a curved space-time. In fact, they do it for more general, not even wave, but okay, let's concentrate on wave operator. And then they have basically constructed this integral kernel for Feynman propagator. So what they did is basically say GF Feynman on a very general manifold. And that construction is more complicated than this, precisely because there you have to take account whether it is positive frequency or negative frequency. And in a general manifold, you don't have really the notion of positive energy and negative energy. So you have to do some very intricate way of mathematics to understand it. And Hurmander basically invented the device, what is required. And if you look at their paper, this problem was suggested to him by Whiteman, who was one of the father of Whiteman quantum field theory. So there has been very interesting interplay between physics and mathematics, at least in PDE, and of course other areas as well.
Onirban, I had a question at this stage.
Sure.
Can I ask it? Okay, so so you have written down this equation u of x is equal to there are two summands on the right hand side. So when you write nabla sub n gxy, you're saying that n is a vector field, right? And what is
it's
there?
a vector unit normal vector field along your Cauchy surface.
Yeah, but whatever you have inside this bracket, is that a vector field as well, or what is that? That's an operator, right?
No. So that's basically the integral kernel of causal propagator. Sorry for my handwriting. I am not very good at tab. So
Okay,
this is
so
basically G, you see, this is the causal propagator and it has this integral kernel G.
So you're taking covariant derivative of operator. How do you define it?
Of integral kernel. So this is a distribution, actually a bidistribution, and I am taking covariant derivative with respect to its second variable. So it's a distributional derivative. Since you want to mathematics, this is a distributional covariant derivative.
Yeah, but you know, in GR, what we do is naturally we take covariant derivative of tensor field, and this is how do you define such a
okay, that's
covariant?
actually yeah, more integrated. So for a distribution or in general integral kernel. Okay, let's go a bit deeper in distribution theory then. So
I don't want to digress. Actually, if you have time or if it's relevant to you, what you are saying, you can spend some.
It is relevant if you, yes, exactly. If you want to know really this object, but structurally
yeah, exactly.
It is not. Yeah, maybe then I can comment later.
Yeah. So I don't want you to spend time on this digression.
But yeah, that
so,
is really this mathematical sophistication one needs to understand, because this object, as you raise, yes, how to deal. So you need to define. So just maybe give a short answer. So in GR or the differential geometry, what we do is to taking covariant derivative of smooth objects, right? Functions, tensors, spinors. And when people start working in PDE, then they found this smooth object are not sufficient. Historically, it's by Sobolev and then Schwarz. So the theory of distribution is basically invented by Sobolev, but it was not known because of this political reason, and it's attributed to Schwarz. So Schwarz basically defined that the way we define differential calculus can be extended in the level of distributions. And then you can have more general situation, like you can handle non-smooth object like Dirac delta. So although Dirac invented it, that time distribution theory was not available. I don't know whether in his lifetime Dirac knew about this work in PDE distribution theory, but now we have a full-fledged developed distribution theory, and you can extend all smooth object in certain non-smooth setting, and the distributional calculus or distribution theory basically do this. So you can differentiate a Dirac delta, and to understand it, you need this distributional idea. So maybe that's the story, but yeah, I'm not going technical. Maybe later if I have time. Okay.
Thank you, Onirban.
You're welcome. Okay, so now we have been lots of talking, maybe the last structure from classical mechanics. So what we have found so far, we have found that if you start from a globally hyperbolic spacetime, you have a canonical advanced and retarded propagator or Green's operator. And then out of this advanced and retarded, you can define causal propagator. So everything is geometrically and naturally and covariantly. So everything is global, even not any coordinate system has been used. And using that, you can also write your Cauchy problem. You have this nice picture. So why it is helpful? It is helpful because now we can see what is sort of geometric structure we have in the space of solutions. So we consider compactly supported functions again. And then using this G, we can define something like this. So U, V maps to, okay, call it sigma. Sigma UV is basically the Green's integral kernel eating U and V. Okay. So now we can show that this is, okay, now we can actually define a L2 inner product on this space, like C infinity M. Infinity, sorry for my handwriting. C, and this is defined U, V, just function. U, V, D, volume, G, X. So it's just a pointwise product of functions integrated over manifold.
I think Jawad has a question.
Yes.
Jawad, would you like to ask the question?
Yes. So it is based regarding about this Feynman propagator that you said that this positive frequency solution and negative frequency solution. So can I attribute them to the usual particle that we find when you do it in the Minkowski spacetime? I mean,
yes, you can. So for Minkowski space, it's reproduce what we know from physics.
Right, but in this globally hyperbolic manifold, can we interpret them as like my particle with some energy?
No, because there is two problems. There is no notion of particle in a globally hyperbolic manifold. Because to define particle, you need Poincare group, and there is no Poincare symmetry on a Lorentzian manifold. You only have diffeomorphism symmetry. So there is no irreducible representation of Poincare group, so no particle. And if you want to look more physically, then Unruh effect basically tells that there is no invariant notion of particle. And now regarding positive, again, there is infinite choice of Hamiltonian because of this infinite choice of foliation. So there is no natural Hamiltonian and no natural choice of energy. Even more severe, energy is itself a coordinate independent concept. So you can say, okay, this is energy blah in this coordinate, and then I do some weight coordinate change, and then it will be a different energy. So the notion of energy is not a good thing in curved spacetime.
I mean, the notion of energy is dependent on the fact that we need a time-like killing vector, right? Otherwise,
precisely.
a global,
and you are in a
global exactly. So a global Hamiltonian cannot be defined. Otherwise.
No way. So that's a stationary case. So if you are in stationary, so basically stationary spacetime is the last spacetime where you have notion of Hamiltonian, some notion of particle. Still, you don't have a Poincare group, but still you have a killing-like time flow. So you can define some notion of particle, but that's the last. If you just go more than stationary, then no particle, no Hamiltonian, and yeah.
But we have a globally time-like oriented spacetime, right?
Yeah, but to define a Hamiltonian, you need time-like killing vector field. So killing is very important, yeah?
Okay.
Okay, good. So in this space of compactly supported function, we can define this bilinear form sigma using the causal propagator. And now we can also define a L2 inner product on compactly supported function in this way, just pointwise multiplication. Oh, sorry, it's a complex conjugate. So maybe this is more proper notation in physics. And now with respect to this L2 inner product, the causal propagator is just anti-Hermitian, okay, or anti-symmetric. Now, what does it say? It says that sigma is a bilinear form, okay, and sigma is anti-symmetric. Now, if you are from classical mechanics or geometry, whenever you see a bilinear antisymmetric form, you remember about something, which is a symplectic form. Now, sigma is not really a symplectic form. Why? Because sigma something with a few vanishes. To have a symplectic form, you need non-degeneracy. And this non-degeneracy is not here. So you can't have a symplectic form, rather you have something called weak symplectic form. Okay, so the Green's operator.
I don't understand what your sigma is. Can you please explain a bit? I think I missed that point.
Is a weak. This is a symplectic form. This is a bilinear form out of Green's operator, and since Green's operator is antisymmetric by construction, so sigma is also antisymmetric, but sigma is not degenerate because it can be zero in this situation, and there is a generalized notion, and this is called weak symplectic form. Okay.
So you mean it's not non-degenerate, right?
Yeah, so I have to only relax this degeneracy condition because it's not true. Yeah, I can't do anything. It's just not true.
Right.
So basically, I'm not imposing anything. I'm just analyzing what the structure has given to me. Okay. So then we have actually a weak symplectic form. That means in classical mechanics, the whole talk is basically tells that in classical mechanics, we have a canonical weak symplectic form. And if you have a canonical weak symplectic form, you can quantize it. And that's the last part of the talk. QFT. So we define quantum field now without using any of this heuristic argument. So this is a distribution from compactly supported function to some algebra. And now which algebra you will see shortly. But there is a reason why I'm not telling which algebra. So this means I take, and this is linear. So I'm taking a linear real quantum field, which means that if I have C is just some real number, then for all this, CF maps to P, CF equals to C, CF. And it must satisfy Klein-Gordon equation in a distributional sense. What is meant by that? Phi, it will answer this earlier question. This is true, yeah, and this is called distributional derivative. Now you can bring it before, then it acts on distribution, and then it will be a dual depending on your form and so on. I'm not going there. So if you write it before in appropriate sense, then it's called a distributional Klein-Gordon operator, because then it acts on a distribution. And in the earlier equation about Green's operator, it was acting in the same manner, okay? And now our favorite canonical commutation relation. So F, oh, sorry, one more, real condition. So phi star. So in physics, usually we use dagger, but I'm not using it just in maths community. It's not, it is for different purpose. So it is complex conjugate. And now our favorite F, G, commutator, I, symplectic form, G. So now we have a commutation relation, and this is a star algebra of canonical commutation relation. Yeah, I'm not going what is the definition of a star algebra and so on, but now you can, so this is the quantization in a globally hyperbolic space-time without using any coordinate. In fact, this is completely global, as you can see. And now the natural question I expect, how about what we read in physics? And the answer is that now, by this distribution here, heuristically, that's why I'm writing in a different color. Heuristically, it means you are doing this thing. Phi of x, f of x, d volume g of x. Okay. If you admit this, maybe it's not a good idea. I write still this way because phi of x is a distribution. A distribution may not make sense pointwise, like quantum fields. And then this relation looks like this. Phi x, phi y equals to I g xy. And you will find this expression in Isaacson-Zuber's book, or maybe any other, or many other physics book. So you see that from a global way, how can we reproduce the usual canonical space-time commutation relationship? And if you want to go to equal time, then you just take the Cauchy data, and then you can do it. Maybe I just write, so K L, sorry. Cauchy data, Cauchy. Then you can do the same thing. Now you define quantum field on a Cauchy hypersurface. K quantum field in a different or same Cauchy surface, doesn't matter. L. And then you have a symplectic form defined on a Cauchy hypersurface. L. And this will reproduce equal time commutation relation. So yeah, thank you very much. I'm sorry to overtime a bit. Yeah, I'm free to answer any question, provided I know the answer.
Thank you so much, Onirban.
So I have a question.
Yes, please.
I'm not sure. I mean, what would be your take on 0-point energy if we do, the quantization in this covariant manner? What would be the status of the 0-point energy?
It's more or less same. So what we do that, so this is everything done this way. And now you can, so we have the normal ordering in our usual physics. You can do the normal ordering again in this covariant way, okay? And if you do the covariant normal ordering, then the 0-point energy situation. So get solved the same way as in physics, because you are not comparing the exact energy, rather you are thinking the energy difference. And the exact energy is not really the right thing to ask in this setting, because we have coupled the system with gravity. And when you have coupled the system with gravity, then the total energy, the notion of total energy is not actually well defined. So again, the Hamiltonian notion is again coordinate dependent or slicing dependent. You need asymptotic free system. And if you do all these things, then you can do Hamiltonian and 0-point energy. And then you can do this normal ordering, and then it solves the same way as the usual physics, but in a global way. You don't use any coordinate. You don't need to use any coordinate because you have this causal propagator, which has better global, not better, I would say it has the global property which is required to do that. In fact, you can do the full causal perturbation theory using this global way. This is called Epstein-Glaser perturbation theory, which has been done for Minkowski historically in 70s. And then around 2000, it started from Friedenhagen and Brunetti. And then finally, this program is done by Hollands and Wald. So maybe it's the point I should comment a bit about the references to the first Hollands Wald. They have actually constructed renormalized Dyson series for phi to the power n theory in a globally hyperbolic spacetime in 2001 and 2 and 3 papers in 3 years. And they more or less nailed down everything. There was one gap, and that was also solved recently, I think 2017. But the gap was really minor. So they assumed something which is not necessarily to be assumed. Apart from that, the construction is right. And so you will get this construction and all this thing in their nice review. And it's a nice thing that it starts from very physical motivation and gives all the mathematical, not all the mathematical details, but quite some mathematical details. If you want more mathematical idea, then this Friedenhagen-Reisner, you will find more mathematical. It's like a structural thing.
Okay, great. Thank you.
You're welcome.
Do you mind if I follow up with you later on these?
No, sure. I'm happy. I mean, that's one of the reasons to organize a seminar. We would like to talk more.
Thank you.
And carry on.
Anyone else has any questions?
I have a question.
Yeah.
In fact, I have a couple of questions. So can you please go down to, towards the end of your slides? I have a few questions regarding the algebra that you are. So you want phi to be a homomorphism, right? Or something like that?
It's just a distribution. So it's a map which is continuous in suitable topology. So this space of compactly supported function has inductive limit topology. And then you can define a topology on space of distribution. So this belongs to, this is the Schwarz notation, space of distribution. And this has a topology, it's called Hurmander pseudotopology. So in this topology, phi is continuous mapping from this to an algebra. So you don't need to CCR algebra. You can consider Weil algebra. Then it's a C-star algebra. In some sense, C-star algebra are better because they have norm. And then from C-star algebra, you can derive classical commutation, canonical commutation relation.
So it's a non-commutative C-star algebra, right?
Yes, it's a highly non-commutative algebra because of this precise symplectic form. Okay,
so now the question is about this commutator that you have written down there, phi of f comma phi of y. So this commutator is written in terms of that product of the algebra, right?
Yes.
It's like the star product that you have there.
Exactly. So what is written here, since I don't know, I didn't actually spell out. This is the star algebra with some parameter h cut, which can be physically interpreted with reduced Planck's constant, but not necessarily, and minus the other way.
Okay.
And this is done using the deformation quantization.
That's right. So now the whatever you have written in the just now, is it the same as phi of f times g?
Sorry, where?
So you have written phi of f star phi of g. Is it the same as phi of phi times g?
No way. And that's because this is a distribution. So yeah, so your question is that can we write fg equals to no way. That's the whole issue of renormalization. So here I haven't talked this because of technical reason. So you can't multiply two distribution pointwise in general. Okay. So when the support of f and g coincide, this multiplication is undefined. And that's in physics, we know this is basically where the renormalization stems from. And now question is that what can we do, or what has been gone through this thing? The answer is that, again, the guy Hurmander, who basically did all this foundational work of distribution, not all, but quite a large extent. So he found out what is the necessary and sufficient condition for two distribution to be defined pointwise. Just very different general question. You have two distribution, say phi and c, you want to define their pointwise distribution. So in general, it's not possible because—
You mean pointwise multiplication of the distribution?
Yeah, pointwise multiplication of distributions. So it is not in general possible. And in quantum field, we encounter in the form of renormalization. So Hurmander asks more general question, not quantum field, just any distribution. And that's not possible. So he found what is the necessary and sufficient condition. It's called Hurmander criterion. Hurmander criterion. To write this, you need a concept, something called wavefront set, which I haven't talked at all about, but immensely important in quantum field theory or even distribution theory in general. So loosely speaking, what is the problem? So maybe I come back to the question that smooth and distributional setting. So say we have a manifold M or even Rn, and a function is defined on it. And by which we mean that we have this blue thing. For each point of the manifold, it maps to some real number. Okay. And if it is smooth, then it means it's smooth in the sense of differential geometry. Now, for a distribution, very horrible situation can happen like this. Or even our favorite physics distribution. So this is Dirac delta, say at point A. Okay, so Dirac delta cannot be differentiated in usual sense. No way, you can see. It's just not possible. Okay, and now you can have two Dirac delta, yeah, if you want to say another Dirac delta at this point, or maybe another distribution in this point. So what Hurmander found, it is not sufficient only to know which points these are irregular or non-smooth. So if I try to explain a bit, Dirac delta is non-smooth only here, right? Apart from everywhere, it is zero and smooth. Okay, what about this horrible thing? This is a smooth more and less here, more and less here. Don't take it literal sense, just trying to give an idea, more and less here. And then the green parts, these are maybe like this thing. Okay. Okay. So Hurmander found something very interesting and very important. What he found, like this is the red or the brown lines are not sufficient. You only also need the direction which this is non-smooth. Maybe an example is better. So say you have a staircase and you want to write up. Then you will find the step function, like your every step is a step function. So if I like this, you are coming from this direction, you will see, there is abrupt change. Okay, very good. But if you move in this direction, you will never see there is any abrupt change. So Hurmander tells that you have to say which point this is irregular and in which direction. So you also have to tell this direction. So point plus direction. You have two data needed. And if you do in a proper sense, there are some definition using Fourier transform, then you can do it. And this is called wavefront set that is invented by Hurmander and also Sato in context of algebraic geometry. But Hurmander's definition is more general. I mean, it applies to more general situation, but essentially same concept. And then in terms of wavefront set, which is written WF, and this wavefront set is nothing to do with the wavefront set of a wave that we know in physics. It's another terminology which encodes this information. There exists some condition like this two distribution should have, loosely speaking, I'm not writing very properly, have so their wavefront set should not should be opposite to each other, something like that. Okay. And in this setting, you can define product of distribution. Okay, so it's done everything in the context of pure maths, no physics. And then what people found, especially Friedenhagen and Brunetti, and also this Lorentzian world, that a special case of Hurmander's criterion occurs in quantum physics. And then they used Hurmander's idea and formalism to do this Epstein-Glaser renormalization in curved spacetime. So back to the question, in general, this is not equals to that because of UV divergence in quantum field theory, which is mathematically encoded that this is a distribution here. So does it answer the question?
Yeah, sort of. But when you write this commutator to be equal to, so can you please go up a little bit? So when you're writing this commutator on the left-hand side, phi of f, comma, phi of y, you assume this, these nice behaviors of the fields, right?
No. I actually I have hidden the whole distribution theory and wavefront set discussion, because it will need actually a whole entire lecture. Because if you want to define this thing, I have cheated. So I haven't defined so I haven't told that what is the support of f and g. So this is in this form, what I have presented is true if their support doesn't touch each other. The moment their support touch, the UV divergence issue comes, and then you need the whole machinery of wavefront set or the renormalization business to define that. And this has been done already in Brunetti, Friedenhagen, and Holland's world. And so it has been done, worked it out.
So when you're writing this commutator to be equal to I sigma, this bilinear form that you have introduced earlier, then you assume that the support of these two things are, non-intersecting, something like that.
No. Here there is no problem because this is in classical level. So I define it here. You see. So here they can have same support. They can have same support, no problem, because this is G is a distribution and these are function. So if function have same support, there is no problem. Problem comes when two distribution have same support. And so there we are not multiplying any distribution, just one distribution G. Okay, so if I write in rate, this is distribution. That's the hard thing. U and V are function, no problem. Here comes the problem because we are multiplying two distribution. Yeah,
right.
This is the problem.
Yeah, so that's what I am asking, that when you are writing this, you are assuming that your distributions, have those nice properties.
No, I have, as I told, I haven't. So if you assume that, then what I have presented is right. But in general, you don't need to assume that, but then you have to talk about the whole wavefront set business, what I haven't.
Okay, all right.
So it is so that was in general, but then you have to tell what is the wavefront set condition and so on, the UV renormalization.
Okay, I get it. So now the last question is about the space of solutions that you discussed a while ago, probably in the previous slide.
Yeah.
The where you define this weak symplectic structure because of the lack of the
property actually.
Non-degeneracy you don't have.
Because of non-degeneracy, I need weakness, and symplectic forms comes from the fact that this is antisymmetric.
So under these conditions, the space of solutions, what structure does it have? Do you have a name of that structure?
This is just called weak symplectic form. So so you can say, oh, you mean whether this has any name, like
yeah. So because I have not encountered any such.
No. So what you consider this actually? So an equivalence class. Okay, so this is actually a this is just a topological infinite dimensional vector space, and no, I don't know any specific name.
Equate with that weak symplectic form, right?
Yeah, it's just natural. Okay, everything is globally naturally comes.
Thank you, Onirban. Thank you.